Welcome to Study Loop.
All right, hello. So today we will be talking about drawing a few different kinds of Lewis structures. So we have a few examples here. The first one is silicon tetrafluoride. And I just want to go through the steps of drawing a Lewis structure first before we go through the rest of the examples. So just to recap, the steps for drawing any Lewis structure are first, we want to determine our central atom. Central atom. Okay, and that is going to be the element which has the lower group number. So whichever one is in a lower column, lower numbered column. So I've circled the two here, silicon and fluorine, and we see that silicon is in a lower group and therefore will go in the middle. And then we can arrange the four fluorines around our silicon, like so. All right, the next step is to determine our number of valence electrons. So the way we determine the number of valence electrons is we just add them for silicon and then for the four fluorines. So for silicon, because it's in the same group as carbon, and we can see that it will have 2 of the 3s2 and 2 of the 2p2 electrons, and then therefore you add those to determine the valence electrons. And I apologize, I meant 3s2 and 3p2. So therefore, silicon will have 4 for the silicon, right? And then we know that, like all of the group 17, the halogens, all of the halogens will have 7 valence electrons. So we have 7 times 4 because we have 4 fluorines, and that gives us a net total of 28 total valence electrons. So if we add those two together, we see we have 32 total. Now the next step, step 3, is to draw a single bond between the central atom and each of the surrounding atoms, like so. And then we can see that because we know that each of the bonds contains 2 electrons, one shared by each atom in the bond, we have 2, 4, 6, 8 total right here. The remaining electrons will be filled in lone pairs. That will go in the valence shells of each of the atoms, right? So we'll start with the surrounding ones, and then whatever's left we'll put on silicon if we need to. Although you may have noticed that since silicon already has eight electrons through the 4 bonds it forms, it is all set with its octet. So we're all good to go with silicon, but we need to take care of the 4 fluorines. So I'm going to fill out the lone pair electrons in blue. So we have 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. And then I should mention we have the 7, 8 through the bond. 1, 2, 3, 4, 5, 6, 7, 8 once again with the bond. 3, 4, 5, 6, once again 7, 8 with the bond. So now if you just see, if you take into account each of the lines as being, I'm sorry, that should not, that's an extra dot, I apologize. So if you just look at each of the lone pair electrons plus taking the bonds as meaning 2 electrons, you can see that each of the fluorine atoms also have 8 electrons each. So if we add them all together, we have 8, 8, 8, 8. That takes care of the 8 that are also being shared with the silicon through the 4 bonds, and therefore we have a total of 32 electrons. And just to confirm, the other way to look at it is to make sure that each of the atoms have a full octet, and they do. 2, 4, 6, 8 here, 2, 4, 6, 8 here, 2, 4, 6, 8, 2, 4, 6, 8 adds to 32. And we can also confirm with silicon as we did earlier based on the 4 bonds. We don't have to do this additional step here, but sometimes you may, if your central atom does not end up with an octet, you will have to then transfer one of the lone pairs to form a double bond. And we may see that in a future example, but for here, this example, we're all set. Okay, the very next example, we'll go through this a little bit more quickly now that we've gotten through the rules, is selenium dichloride. So once again, we look at whichever one has the lower group number, and in this case, that's selenium. So selenium goes in the middle, and then we will basically draw our chlorine atoms on either side. I should note here that it does not actually matter where I draw these chlorines in the Lewis structure, because the Lewis structure does not represent the actual 3D structure of our molecule. It just represents how things are bonded. So we can actually draw this however we want. We are not intended to find any sort of structural information necessarily from a Lewis structure alone, and that's an important point. So the Lewis structure is actually a misnomer. It's often called a Lewis formula. I'll write that down just as a clarification. So now that we have these here, next step, our step 2, is to determine the number of valence electrons. So our selenium is in the same group as oxygen, and we know oxygen, like sulfur, has 6 valence electrons, so we have 6 here. And then we have 2 chlorines, so that means we have 7 times 2, giving us 14 total electrons. So if you add those together, you get a total of 20 electrons, valence electrons. The first thing we do then is draw a single bond between the central atom and each of the surrounding atoms, and that accounts for 2 electrons each, so 2, 4. Now the remaining 16 electrons we will spread out on lone pairs. So we start with the peripheral atoms first. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So if we now count, first of all, both our chlorines are all set. We have a full octet for both of them. Are we good with selenium though? No, because we only have 2, 4. We need 4 more electrons, and if you notice, we have 8 and 8. That's 16. We still need 4 more to get to our 20. So we can then draw those lone pair electrons like so. So you might be asking, why don't those just form a double bond? And if they do, what ends up happening is that you've exceeded the octet for chlorine. Now, and chlorine, like any halogen, cannot form double bonds. That's an important fact, and that's kind of one that does not have any exception really, in that none of your halogens will ever form double bonds. So in this situation, we see we're all set because we've given chlorine the 1 electron it was missing from its 7, and we've given selenium its octet as well, and therefore we've completed our Lewis structure here. All right, our last example is this molecule with we will now first figure out which one is the central atom, and once again I'm going to circle carbon, oxygen, and fluorine on the periodic table to help us determine that. So we have carbon here, we have oxygen here, we have fluorine here, and we see that since carbon has the lowest group number, it goes in the middle. And also the problem statement explains that, but this was given as a hint because we have 2 different heteroatoms. So heteroatoms, I say, are anything that's not carbon or hydrogen. Because we have oxygen and fluorine, this was given as a clarification. So then once again, we can arrange our heteroatoms however we want. So we have our oxygen, we have our 2 fluorines. Again, it does not matter how I do this because we're not getting any 3D structural information from this. The next step is to calculate the number of valence electrons. So we have 4 from the carbon, we have 6 from the oxygen, and then we have 7 times 2 for the 2 fluorines, giving us 14 there for the fluorines. Okay, so once we have this, we see 4 plus 6, 10, 10 plus 14, 24 total valence electrons. So once again, first step, we draw single bonds, 1, 2, 3, as so, and then we fill in the rest with valence electrons. So we see, lone pairs as valence electrons on the surrounding atoms first, right? So we have 6 here, so 6, we need 18 remaining, and the 18 remaining can spread themselves out. So we got 1, 2, 3, 4, 5, 6, like so. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now that takes care of our 18, right? And if you notice, we have 8 here for oxygen, 8 here for fluorine, 8 here for another fluorine. That 8 plus 8 plus 8 gives us 24. So those are 2 ways to check it. Either you count the blue electrons that you've dotted that are going beyond the ones that are bonded, and then you make sure that they calculate to this number, or you just determine, you kind of split the single bond in 2 and see if you have 8 for your peripheral atoms. And once we've completed this step, we can see that there's an issue because carbon has not completed its octet, right? We have 1, 2, 3, 4, 5, 6. We're missing 2. We can't put a lone pair on carbon because there's no orbital for it to go in. So what we need to do is, this is that extra step I mentioned when we talked about the first example, where you're going to have to move one of the lone pairs to form a double bond. Now you may be asking, which one do we move it from? And if this goes back to what I said in the previous example, where any halogen can only form single bonds, so it must come from the oxygen then. So what we're going to do is we're going to move this double bond here, and I'm going to erase it to make sure that's not confusing for us, right? So I've erased that, and that is going to form the second bond here. Now let's go back and do our count. Do we have a full octet for everything, and do we have the total 24 electrons? Let's take oxygen. 1, 2, 3, 4, and each line representing 2 electrons, 5, 6, 7, 8, all set with oxygen. And fluorines, the same as before, so they're all set because we have 8 and 8 if we split the single bonds. Now let's make sure carbon's okay. We have 1, 2, 3, 4, 5, 6, 7, 8, and we're all good here too. So I'm just going to make sure that, yes. So I hope that this is clear. You just want to, this is just the simple